Dear students, today we'll see what do we mean by parallel resonance. Now, before this, in our last class, we have seen what was series resonance, and today we'll see what is parallel resonance. So, we'll have today's topic as parallel resonance, and in that we are going to see what is parallel resonance, plot of parallel resonance, characteristics of parallel resonance, a condition for parallel resonance, expression for frequency of resonance, and then we'll see one experiment on parallel resonance. So again, we'll start first with what is resonance. So resonance occurs in electric circuits due to the presence of energy storing elements like inductor and capacitor. So it is the most important components, that is inductor and capacitor, which are energy storing elements which are used in circuits to exhibit what is resonance. Now this a concept, it is the fundamental concept, it is a basic concept which is used in radio and TV receivers. So we have our radios and TVs at our home. So in that, whenever we tune to a particular station, the tuning of a particular station, that is, you are giving an output for a particular frequency, and that particular frequency output is the basics of why we have studied or why we are studying resonance. So resonance will be the circuits which will allow you to tune to a particular frequency. They will allow you to tune to a particular desired station. Okay, that means whichever station you want to hear on radio or whichever channel you want to tune on TV, that is, you're tuning to a particular frequency. You're selecting a particular frequency, and that is what is the basis of resonance circuit. So because of resonance concept, we are able to go to applications such as tuning of particular frequencies in radio and television applications. So in a resonance, as we have seen earlier, we saw two types. One was series resonance and one was parallel resonance, and the difference was made because of the connection of inductor and capacitor in series resonance and in parallel resonance. So let's start with what is parallel resonance. So a parallel resonance, one definition we can say that parallel resonance means when the circuit current is in phase with the applied voltage of an AC circuit containing an inductor and capacitor connected together in parallel. So if you are having inductor and a capacitor connected together in parallel, and in that circuit the current which is flowing through the circuit is in phase with the applied voltage, then a resonance takes place, and because the circuit is having parallel combination of inductor and a capacitor, that resonance will be called as parallel resonance. The other way to look at the parallel resonance concept is that a parallel circuit are consisting of inductor and capacitor, in which the inductive reactance and capacitive reactance are equal and obtain maximum impedance at the frequency at which the circuit is resonant. Now what does this mean? Now we will have in this circuit inductor and a capacitor in parallel, and here we are going to apply the voltage. Say this will be the voltage, AC voltage with variable frequency. Okay, now this is what we are going to have, and here we are going to have the output. So output will be taken here. So this will be the output what we are going to have. Now the inductor is one which will have opposition to the flow of current, which will be called as XL. Now XL will be given as 2 pi FL, where F is the frequency of the input applied. Now this input, whatever we are going to apply, we will keep the input voltage constant and will change its frequency. So here this is what AC input what we are going to apply here, and number of cycles per second will give you the frequency. So if the frequency increases, the inductive reactance, that is opposition to the flow of current given by the inductor, will increase. Similarly, if you see the reactance of a capacitance, Xc is equal to 1 by 2 pi Fc. Now in this case, this reactance is inverse to the frequency of the input. So if the frequency of the input increases, this reactance decreases. So there is a inverse relationship between the reactances of inductor and capacitor. Okay. Now we say that when the inductive reactance is equal to capacitive reactance, that is Xc. So here we'll be having Xc. When XL is equal to Xc, at that time the resonance which take place for a parallel combination of inductor and capacitor at a particular frequency, it is called as parallel resonance. Okay. Now here, this same concept of reactance can be viewed in another way, because we have a term called as susceptance for inductor and capacitance. Now susceptance is nothing but it is the reciprocal of reactance. So if you take 1 upon XL, it will be susceptance for inductance. And if you take 1 upon Xc, it will be susceptance for capacitor. Okay. Now here the basic concept very easily says that if reactance is the opposition to the flow of current, then susceptance, which is reciprocal of reactance, should allow the flow of current. Okay, so it is a factor, it is a parameter of inductor and capacitor which is giving you how much current they can allow. So allowing of current. Okay, now this same definition for parallel resonant can be defined as a parallel resonance for a parallel combination of inductor and capacitor takes place when the susceptance of inductor is equal to, that means it is equal and opposite to, susceptance of capacitance. So they will get cancelled out each other. So allowing of current will be minimum in the circuit. The current flow will be minimum in the circuit. And because the current flow is minimum in the circuit at resonant, we say impedance, that is the opposition to the flow of current, is maximum in the circuit. So for parallel resonance circuit at resonant frequency, the current flowing is minimum, the current through the circuit is minimum, and because the current through the circuit is minimum, obviously the other part is impedance of the circuit should be maximum. Okay. So here these are the characteristics of your resonant frequency. Then we'll go to see this circuit of resonant frequency here. So here we see our main concept in this parallel resonance circuit is, if you concentrate on L and C, so L will be in parallel with C. So here you can see this is the inductor L, this is in parallel with capacitor C. Okay. And here we see the applied voltage, whatever we are going to apply. So here we will keep the voltage constant and we will vary the frequency of the applied. So at a particular frequency, the reactance of the capacitance will be equal to reactance of the inductance. Okay, that is XL is equal to XC, or susceptance of inductor, that is 1 upon XL is equal to 1 upon X is susceptance of capacitance. So this will give you the parallel resonance, and in that case what will happen, the current which is flowing through the circuit, this current which is flowing through the circuit, when XL is equal to XC, this current which is flowing through the circuit will be minimum, because the susceptance of both inductor and capacitance will get cancelled out with each other, and the allowing factor of current will become minimum. So the current flowing through the circuit will become minimum. Okay, and because current becomes minimum, the impedance of the circuit, that is the opposition to the flow of circuit, that is Z, will be maximum. Okay, so impedance will be maximum. Impedance is nothing but it is a combination of resistance and reactance for a AC circuit. Okay, so resistance of the resistor and reactance of inductor and a capacitor. Now together reactance and resistance will make impedance, and impedance is again nothing but opposition to the flow of current, and that will be maximum at a particular frequency, that is resonant frequency, and therefore current will be minimum for that. Okay, now this is the thing what happens in a parallel resonant circuit. Go to see the curve, which is very important for parallel resonant circuit. Now this is a graph between impedance. So as I've told you earlier, impedance will be nothing but opposition to the flow of current, impedance versus frequency. So here you can see the graph of impedance versus frequency. Now you can see that when the frequency is lower, impedance is less. When the frequency is lower, impedance is less, and as the frequency increases and reaches the resonant frequency, the impedance here is maximum. Here you can see impedance is maximum, that is opposition to the flow of current is maximum, and again when you increase the frequency, from that the impedance will go on decreasing. So this is the graph, this is the response of frequency versus impedance. Okay, so impedance will be maximum at a particular frequency, that is called as resonant frequency, which is nothing but this parallel resonant frequency. Similarly, if you see the graph for current, now because for particular frequency the impedance was maximum at resonance, here we can show that at a particular frequency the impedance is maximum, so the current is minimum. So here you can see at a particular frequency the current is minimum. So when the frequency is lower, the current increases. When the frequency is higher, the current increases. But at a particular resonant frequency, the current is minimum. Okay. Now this is the graph of frequency versus current. So here x-axis we have taken frequency and y-axis we are taking current. Okay. So this is a graph of frequency versus current. Now students, we will see the phasor diagram of a parallel resonance circuit. Now if you see the phasor diagram for an RLC circuit, now we can see in that the current which is flowing through the resistance will be in phase with the voltage. Now current this is flowing through the resistance will be in phase with the applied voltage, and the current which is flowing through a capacitor will be leading by 90-degree. Now this is current going through the capacitor, flowing through the capacitor, this is leading, and current flowing through the inductor will be lagging. Current flowing through the inductor will be lagging. This is lagging of inductor current. Okay. Now if you go to see the resultant, and if you go to see the frequency at resonance, then we can say that we can have this IR, that is the current through the resistance, okay, which will be in phase with the voltage. And here we can have this component. Now in this component we'll subtract the capacitor current, so this component can be written as IL minus IC, because that is also of the same magnitude but in opposite direction, so this can be IL minus IC. Now we can take a resultant of this, and this resultant we can mark it like this. Now this resultant will be a current which is nothing but IL minus IC plus IR plus IR. Now this is the current which is going to flow at resonance. Okay. Now this is the current which is the resultant current, and this is the current which we can say flows at the resonance. Clear? Then next we will go to see the expression for resonant frequency in parallel resonance. So to get the expression for resonant frequency in parallel resonance, we should first see the branches of the circuit, and in that branches we have to see what are the admittances. So the expression, to get the expression, the procedure starts from the branches. Like the branch of the parallel circuit was, we had a resistor, inductor, and on one arm we had capacitor. Now here we see the L and C are in parallel. L and C are in parallel. Now the a current which is going to flow, okay, which is going to flow here. Now this current will pass through this arm and also through this arm. When it is passing through this arm, the opposition it is going to face is R and also here j omega L, and the opposition phased in this arm will be 1 upon j omega C. Okay. Then if this is the opposition, then what is the admittance? So admittance in the inductor arm will be YL, which will be nothing but 1 upon R plus j omega L. And the admittance of the capacitor arm will be given as YC is equal to j omega C. Okay. Now we know that the total admittance Y will be equal to YL plus YC. Okay. Now in this, if you add them and then if you solve it, you will get a last equation as Y is equal to R upon R square plus omega square L square plus J into omega C minus omega L upon R square plus omega square L square. Okay. Then here we have to take the imaginary term. This is the imaginary term, and this imaginary term we have to equate, because one is giving you the capacitive term, this is the capacitive term, and this is the inductive term. Okay. So these two should be equal to each other. Okay, and this condition will be a resonant condition. So here we see, after rearranging, now in this equation we get the omega as resonant frequency, angular resonant frequency C, which is equal to omega L upon R square plus omega square L square. Now this is what we have converted omega to omega R, because it is the angular frequency of resonant. Omega is nothing but 2 pi FR C is equal to 2 pi FRL upon R square plus 2 pi FR whole square L square. Now if you solve this, we will get the resonant frequency FR is equal to 1 upon 2 pi under root 1 upon LC minus R square upon L square. Okay. Now this is what will be the expression for a resonant frequency in parallel resonance. We can also see the frequency response of parallel resonance circuit. So we can have a response of impedance versus frequency. Impedance versus frequency. So here x-axis you can take for frequency, y-axis you can take for impedance, and this graph will look like this. Okay, so this is impedance Z, and there will be maximum impedance at the resonant frequency FR. Okay, so this is the maximum impedance at a resonant frequency. Similarly, you can have current versus frequency. So in that case, we can have current on the y-axis, current, and frequency on the x-axis. So this graph will look like this. Now there will be minimum current at resonant frequency. Okay, so there will be minimum current at the resonant frequency. So here you can see it is minimum current because impedance is maximum. Similarly, if you go for voltage versus frequency, then we can draw the graph same like we have drawn for impedance. So this will be the voltage and this will be the frequency, and we can get the maximum voltage at resonant frequency. Now from this maximum voltage, if you come down to 70.7% of the maximum, so if this is V max, and if you come down 70.7% of the maximum, okay, that is 0.707 V max, you will get these 2 points, and these 2 points will be nothing but your F1 and F2. Now it is the range where you get the bandwidth. Now this is the bandwidth of the circuit. Now if you know the bandwidth of the circuit, So bandwidth will be given as f2 minus f1. Okay, and similarly, if you want to know the quality factor q, q is given as resonant frequency upon bandwidth, that is nothing but fr upon f2 minus f1. Okay, so this is your quality factor. Now what does the quality factor say? Like, say for example, if this is your graph of current versus frequency, if you draw the graph here, current versus frequency. Okay, so this is your resonant frequency fr, this is 0, this is f, this is current. Now if your q is less, then the graph is wider. If your q is high, then the graph is narrower. Okay, so this is for high q, here the q is high, and for this the q is low, q is low, here the q is high. So quality factor tells you about whether the graph is narrower or the wider graph with respect to the resonant frequency. Then we'll go to see the experiment what we have done on parallel resonance. So here the aim of the experiment will be construct a parallel resonance circuit and plot its frequency response. So for this experiment, what we have to do is we have to first take the circuit, and the circuit will be of this kind. You can take the input from the function generator, and then you can connect the inductor, capacitor and resistor. So here we will connect the capacitor, here we will connect the resistor, and here we will connect the inductor. So our resistor will take it as 100 ohms, inductor will take it as 100 millihenries, and a capacitor will take it as 1 microfarad. So this is 1 microfarad. Okay, and this is what we are going to apply from the function generator V in. So your input voltage will keep it at 5 volt fix, and we are going to change the frequency of this wave, the sine wave, whatever we are going to give from the function generator, we are going to vary the frequency of that. Okay, now with these values, if you find out what is the resonant frequency, so we know that for resonant frequency the formula is fr is equal to 1 upon 2 pi, fr is equal to 1 upon 2 pi under root 1 upon LC minus R square upon L square. If you put L is equal to 100 millihenries, C is equal to 1 microfarad, and R is equal to 100 ohms, then we get the value of FR, that is resonant frequency, FR as 503 Hertz. Okay. Now this says that the input what we are going to give, and when we vary the frequency, the output current will be minimum at 500 and it will be maximum above and below 500. Okay, so here we can see, if you take the readings, you can take it as V in is input voltage. Now it is fixed at as V in is equal to 5 volt, you can take, and then you can have the columns as serial number, frequency in hertz. Okay, you can check output current, you can also check output voltage, clear? So here you can put a meter where you can see the current through the circuit, and you can also check here the output voltage by connecting it to CRO. Okay, now here if you see, if you take the readings 1 2 3 4 5 6 7 8 9 10, the frequency will vary from 100 hertz. Keep the input voltage constant, go on varying the frequency 200, 300, 400, 500, 600, 700, 800, and for that you note down the output current, for each you note down the output voltage also. If you see the output current, the current will be minimum at 500, at this reading it will be minimum. Okay, and then here it is going on increasing like this, and even here it will go on increasing. Similarly, the voltage will be maximum at 500, and there will be go on decreasing, and down also it will go on decreasing. So from this you can draw a graph for frequency versus current or frequency versus voltage. You can calculate the bandwidth, and also you can calculate the quality factor. Thank you, students.